ChatGPT possible. Okay, and then we also have recommender systems. So whenever you do some online shopping and then you see the recommendations, they ask you, oh, do you want to buy these items? Or when you watch Netflix and you have things that they say, we think you will love this. Okay, that's recommender system in play. So yeah, recommender system is related to money directly, right? If you are successful, you have a high success rate, then the companies will get a higher profit. Okay, so I'm just going to give some general examples of supervised learning. So one example will be something like this. Okay, you have a data set. This could be in the form of a graph, or it could be in the form of, let's say, 90 data points, or even 900 data points if you have maybe hourly data, right? Or yeah, it can be daily, hourly, by the minute, and then the objective of the supervised learning will then be, given this data set, do you want to buy or sell? Or it could also be asking you to predict what is the return over perhaps 1 month later, or 6 months later, or 12 months later. So you see that for the very same data set, and even though it's a supervised learning task, we could frame the problem very differently, right? In terms of our target. Just simply deciding to buy or sell would be a much easier problem than if we want to say to predict the return. Because then not only do you want to have an accuracy of whether to buy or sell, you need to know how much movement it will be. Okay, so another example of supervised learning will be like structured data. Maybe you have this kind of typical credit card scenario whereby they say, okay, you're employed for 3 years, you have a certain income, a certain outstanding loan, and then they want to ask you if you will default or not. Okay, then another one will be related to NLP. So you have a text. Chicken rice is a very famous food in Singapore. Okay, so if you come to Singapore, you should definitely try it. Okay, so we have a given input X. Maybe, for example, the chicken rice is not bad, although a little oily. And then the prediction will be the rating. Okay, if it's a scale of 1 to 5, then did the user give this store a rating of 2 or 4 or 5, okay, based on the string. Okay, another example will be the recommender system example. So you watch various shows on Netflix, and then the thing that you are trying to predict will be what is a show that the user will like to watch. Okay, then I'll give another example. So this example is pretty nice. It's actually one of the projects done by one of my students a few terms ago. So in the computer vision class, they have the object detection task where they are trying to have a bounding box across fishes. So you can see this whole thing being predicted in real time, and this is the output of the application. So of course, the application will work for different videos as well. I just use a sample which is given by the students, the group of students. Okay, and then lastly, for the examples, we have what we call the semantic segmentation. So naturally, you will know that this is required if you want the ability for cars to perform the self-driving abilities, then they must be able to understand whether it's a human or a road or a tree and traffic light. So this is part of computer vision, and it's also under the supervised learning task. Okay, so for all these supervised learning tasks, the common thing that we have will be we already know the truth. Okay, we will be able to know the why. Okay, the target label why. Okay, be it for buy or sell, we should know. Okay, when we want to train on this data, whether it would really rise or fall in order to decide to buy or sell. Or in the case of a prediction of how many percent, we should know what's the truth. Right? The same for all the other scenarios. We need to know what is the so-called correct answer. Okay? And then we will train the model to be able to recognize, given these inputs X, I will make a prediction Y. Okay? By giving them the truth, and when we give them sufficient number of examples, they will be able to predict the correct outputs. So these are things that you will learn here. In fact, as early as in your second course in applied machine learning, which is one of the foundation course, you will start to learn this kind of contents. Okay, so just to go a little bit deeper into this specific area of computer vision, right? Just now I was giving just a general examples. So one of the use case also in another course project, okay, the students actually cited a case whereby in a 5-year period, there are some 15,000 pothole deaths in India alone. Okay, so this is their business case. and therefore they want to have computer vision to predict the road defects. So you see the cracks on the road, these are called potholes. And what happens is that when the vehicle drives over it, okay, it's easy for them to lose control. And as a result, there might be an accident and people might die. So the roads are very wide, right? You have 1,000 kilometers or 2,000 kilometers. So the objective is to train a computer vision model such that you can mount it on the car, and as you travel along, you can identify all the potholes. Okay, so now why do I have this slide over here? I'm saying the input is what's on the left, okay? The image itself, which is a scene from the camera. And then the output will be the bounding boxes, where we predict the pothole. So our objective is to train a model. So now we need to take a step back and we need to ask ourselves, how is an image actually seen? So an image is actually seen in terms of pixels. So the image on the left is actually all numbers, and we pass into the model an image. What really happens is we are passing in to the model just a series of numbers. Okay, so an image is seen as pixels. The next thing you need to understand will be what are features. Okay, so features are actually the presence or absence of some visually identifiable features. So, for example, you can have a horizontal line, a vertical line, a curved shape. Okay, these are all features. But when it comes to deep learning, okay, we actually have much higher level and abstract features which we really cannot quantify in terms of English words. So what happens will be we just let the model learn their own features. Okay. Afterwards, I'll give a slide to show you an example of what is a first level feature. And from there, you can imagine, okay, when we come to deep learning, we can have multiple layers and they are really able to learn much higher level features. So basically, when you look at anything around you, okay, look at your computer in front of you now. Okay, look at your cup beside you. Okay, how do you identify that there is a computer or there is a cup? Basically, your brain tells you that okay, this is a computer because it's rectangular. It has the keypads, the alphabets on the keypad, or if it's a cup because it's tall and cylindrical. So these are actually all features that your brain pick up and identify. What happens in computer vision is really the same. Okay, we are just identifying such features. Then the next thing we have to ask, which you will learn in MITB, will be so how is a model trained? Okay, so to simplify things, I will just say that a model is trained by gradient descent and backpropagation. So whenever you have a prediction, you know how good or how bad a prediction is, right? How far it is away from the ground truth. What happens then will be you need to do a backpropagation to change the weights of the model. Okay? When you change the weights of the models, what happens is that it will change the prediction in future. And the prediction will be something that is ever so close, just slightly closer to the truth in one step towards the better direction. And what happens is you train it over thousands of epochs, and after these thousands of epochs, the model moves a step closer and a step closer, and eventually you'll be able to output predictions that are pretty accurate. Okay? In fact, based on 2015, 9 years ago, as of 9 years ago, the performance of image classification actually outperformed human. Yeah, in 2015, computers can perform better than human at identifying whether an image is one of 1,000 classes in the image net. Okay, the humans have something like a 5% error rate, and even 9 years ago, computer vision is already able to achieve an error of less than 4%. Okay, so just to go back to what are the features, okay, I said I'll give you an example, right? So let's take a look at this example over here. Okay, you see that on the left, we have some image. Okay, it's a grayscale image. Basically, this is a scale, that is an image of a SMU campus. And on the right, okay, what happened is we apply a single kernel filter, which is really the things that a computer vision model actually applies to an image. So by simply applying just one kernel, this is actually a sober edge detector, and as you can see, is to predict the vertical edges. Just one single layer, and you can already see that it's able to pick up something so interesting, right? You can see clearly where are all the pillars, okay? All the vertical edges, the pillars, the trees. And you will also notice that it's able to ignore the horizontal edges. For example, the steps. On the bottom right-hand side of the image, you actually see a smooth region and you don't really see the steps. So this is an example of learning the vertical features. So extend this to many different kind of features and extend this to features upon features, and you can see why computer vision works. Okay, so computer vision at each layer, they have many kernels to pick up many different kind of features. And then on these features, they again apply new kernels on top of them to learn higher level features. Okay, so from low level features such as vertical or horizontal edges, we eventually learn things such as curves, maybe the ears or the eyes or the cat tail, the cat paws, and even higher, more complex features that is learned. Okay, so that's really the underlying principle of computer vision. And even though there is so much progress in computer vision for the past 9, 10 years, but this underlying concept remains the same. Okay, for the 9 to 10 years, the underlying concept remains the same. And I dare to say, in the next 10 years, this concept is still a fundamental that you cannot do away with. Okay, so just back to more on object detection. So I'm just showing an example of the students' model in their course project. And when you join MITB, you will get to do various projects and showcase your work. So I'm just using one of their work and showcasing over here. Okay, so you notice that the for example, in the second image on the bottom, okay, there's many boxes. Well, I'm just taking their intermediate outputs, yeah. So you can imagine that when it comes to object detection, okay, what happens is that beneath this model, okay, the underlying truth is that there are actually many anchors. Okay, anchors, which means that they are candidate bounding boxes, things that are potential candidates which the model will then predict to use or not to use. Okay, so the reason why you see many apparently overlapping boxes is because there are many anchors, and the reason for so many anchors is so that we can have a tight bounding box. So this is actually an intermediate step only. Of course, in the final step, if I were to give you such a prediction, it's going to be very ugly, correct? But you also have seen earlier from the fish example that there isn't all this overlapping bounding box. So just want to mention that in the intermediate step, this is what happens in the model, and then people apply something known as a non-max suppression. So in a non-max suppression, they will check for all the overlapping boxes. And if there's a high intersection over union, which is a high overlap, then they will say, okay, so these two boxes are likely to be trying to identify the same thing. And then they will only determine one of the box, they will only keep one of them. Okay, which one? The one with the higher confidence. And they do this iteratively. So eventually, they are able to remove the overlapping bounding box and just get a neat single bounding box. Okay, so these are also the things that you'll learn when you take a computer vision course, which is one of the courses that we offer. And yeah, if you take that course, you will see me over there. Okay, so yeah, just to show another example of students project also in this CS604 on computer vision. Okay, so the reason I show this slide is because at MITB, we don't just teach you the technical things. Okay, we want to teach you the business and the application aspects of things as well. Which means that just knowing the math, just knowing the Python code and being able to build the model itself is not enough. Okay, you must be able to translate the end user's business requirement into a final product that matches the requirements. So what do I mean by this? Okay, in this particular example, okay, the business case was that the students say, okay, they have hours of diving videos and they just want to identify which is a interesting portion. Okay, and how do they define by interesting portion? They define by two aspects. Firstly is there's a large number of tiny fishes. Okay, so on the left, many small fishes over there, right? And you can imagine that once we have a bounding boxes, we'll be able to have many boxes if it's trained correctly. The second thing that they deemed interesting is there's a large sea creature, okay, like a manta ray. For those of you who go diving, you know that this is such a rare and such a beautiful sight that everyone will love to have, right? Or maybe if you have a shark up close, okay, a single image and up close. So the student's original question, the business question was define an interesting slide. Okay, define an interesting frame of the video, okay, or interesting frames of the video. Then that let them to have this definition. And from this definition, then they say, okay, how do I want to identify a frame that have a large number of objects or a frame that have a single large shark, single large manta ray? Then they say, okay, let's use an object detection model. So you realize that the object detection model itself is really not an end. It's just a means to an end. They want to use a model to make predictions on many frames so that from those predictions, then they can identify is there a large number of small items or is there one or two huge items. And from there, what happens is the students then make it into an application. Okay, that will be actually in the following slide. But along the way, okay, let me just talk more about the training process. So you see that in computer vision, okay, and in fact, in anything in supervised learning, people always say, data is money, right? And data is what makes supervised learning possible. So what happens is once you come to computer vision and supervised learning in general, there must always be augmentations, okay? Because you could never have too much data, right? More is always good. So what is the whole idea about augmentations? Okay? Augmentations is about changing our inputs slightly, okay? Such that it could be like a bit blurred or changing the color, the depth, the angles, the whether it's zoom in or out, the aspect ratio. Why do we actually do all this? Okay, so in computer vision, you know that a photographer could take the photo in many ways, right? He could take a photo with a zoomed in object, or he could have tilted his camera. He could have taken the pictures in low lighting or in very overexposed conditions. So these are all possible scenarios that we want the model to be able to learn and pick up and identify as well. But in our training data set, we might not have everything. So what we do is we deliberately introduce all these changes. Okay, so I gave just a couple of examples. Translation, which is just shifting left, right, or up, down. Scaling, so just like zoom in or out, you can smash it to be tall and thin. Rotating, okay, just turning, and then you can make it blur. What happens if we just pass through a filter and we can make it blur? Okay, hue and saturation is in terms of the color, which okay, let me just show over here. So now you can see there's different aspects of a color. We define a color in terms of its value, okay, how bright or dark it is. And the saturation and the hue will be along the circle. Okay, not to worry too much about all this, just to understand that you can define a color using different parameters, and we change all these parameters so that our image looks different. Okay? Everything is just mathematical operations. Okay, so back to this augmentation, right? Because we want to have many different kind of images so that our model will have seen a wide variety of examples, and then they'll be able to make good predictions even in new cases. Okay, so when we do augmentation, okay, it will be required for all the different frames. And all this will be done by Python. So you do not manually, open a Photoshop and change each image. No. In fact, all these operations are actually done mathematically to images that had already been transformed to tensors. So the reason why we actually show this is just for visualization purpose. It's just to that you understand, oh, this is the equivalent of getting, 6 different kind of images. But in reality, when we do augmentation, we don't create 6 new copies of the image. All of them are just mathematical operations on tensors. Okay, so yeah, I just take a single frame of the video just to show an example of the possible outputs. Okay, and then with their corresponding percentage confidence. So back to earlier when I say that computer vision and object detection, they are just a means to an end. Okay, so the student actually have a whole pipeline starting from number one, where they actually collect the data, which is collect videos. They are actually a group of divers, so they are interested in videos and videoing their diving trips and collecting from YouTube and online open source data. So after they collect that data, which is just the videos. The videos means that they have many, many frames, right? And then that's where they build the object detection model. You might be thinking, oh, do I actually train an object detection model on the video? Well, yes and no, because the truth is that the object detection model is actually just trained on many, many frames, right? And then, of course, you have to selectively use the frame. There's 60 frames in 1 second. So do you really want to use all 60 frames? Is it relevant? So there's something that they have to think about as well. So after getting all this data, what they then do is they have to train the model and fine-tune the model. Because the choice of hyperparameters can make a big difference. You have the exact same code, but you fit in different inputs, different hyperparameters. And it can mean the difference between day and night. It can mean the difference between something that works well and something that is totally, unusable. Okay, after they get the model, and what they then do will be they want to do what I call post-processing, okay? Or rather what they call post-processing. So remember that the object detection model is just there to give the bounding box, but that doesn't answer their question. Their question was, which is the frames that are interesting? Many fishes, or a single large manta ray, shark, whale. So from the object detection model, what they do is they actually have an application such that they take in the input, which is the video, convert the video into many frames. They run the model on each and every frame to get a prediction. Then from the prediction, they need to post-process. Why do they post-process? Because they want to say, okay, those predictions where there's no bounding boxes, okay, we discard them. And those predictions where there's many small boxes, and we say, oh, these are the frames where there are many small fish. And in frames where there are just single large boxes, then you can identify and direct it accordingly. So from this, the student are able to identify from a given video whether is it a short snippet of many small fishes or whether is it a short snippet of having large manta ray, large shark, and so on, large turtles. Okay, so you get to see the whole process, and all this happens in a single course. So we always want to emphasize in our courses not just about building the model, because nowadays with open source, getting a model alone is not enough. It's how you translate the business case and how you provide an app to the end user, right? How you deliver the solution. Okay, so I understand that I have about maybe 5 minutes or so left, and I would like to just conclude this masterclass with the remaining 5 minutes talking about reinforcement learning. Okay, so in reinforcement learning, no matter which course that you attend, okay, you will definitely see this image. Okay, this is like the image in reinforcement learning. Okay, just to give you a quick teaser, of course, you will not do justice to this whole very big domain, but just a teaser. Okay, the fundamental idea of reinforcement learning is you want to interact with the environment. So you are an agent. The agent is able to make decisions. Okay, and these decisions will affect the environment. And in turn, the agent will sense a reward from the environment. So there are a few key aspects about reinforcement learning, which I hope that you take away at the end of this session. And again, these fundamental principles have been there for the past 10 years. It will still be there for the next 10 years. Okay, so what are these fundamental principles in reinforcement learning? Okay, the first is that your reward and your state that you receive from the environment is beyond your control. Okay, so just as we can expect many things in life is beyond our control, same thing reinforcement learning models the environment that way, which means that for a single action, okay, we can take the same action, but we might end up in a different state and we might get different rewards, okay, for the very same action taken. So there's some stochasticity involved, it's non-deterministic because there's a randomness involved, right? You never know. It's like you can study hard for an exam, but you never know whether will you get an A plus or A minus, things like that. Okay. The next thing that is fundamental to the idea of reinforcement learning is that we want to maximize not just the immediate reward, but all the future rewards sum up until the end. Okay, so what happens is we need to account that present rewards are generally worth more. It's just at the time value of money, right? $1 today is worth more than $1 in 10 years' time. So the same for rewards. And what happens is we want to maximize the sum of total discounted rewards all the way until the end of the episode if it ends, or all the way until infinity if it doesn't end. Okay, so the example here would be, for example, if you might not like to study when you are young, okay, but you still study nonetheless. So you may have a negative reward, but you know that when you grow up, you know you can be a doctor or a lawyer or a data scientist, and you can have a good job, right? So that's where you get a big positive reward. Okay, so you want to think long term and maximize your total rewards. So I first mentioned things beyond your control. Second, maximizing your total reward. The third thing, okay, that is fundamental in reinforcement learning is that your choice of action matters. Okay? Your choice of actions, so A, your choice of action will affect the state that the environment makes you in subsequently. And within that state, you have a limited range of possible actions to choose from. Okay? That is really why it's so important to choose the right actions and to be selective. Okay? So I always give an example. For example, right now where I'm sitting, can I say that I choose to be the Prime Minister of Singapore tomorrow? No, I cannot. Because I'm not in a state that allows me to be the Prime Minister of Singapore. Correct? So I can choose different possible jobs, but being a Prime Minister is not one of them. Okay? And why is this so? It's because when I was young, 20 years ago, 30 years ago, I've already taken actions which led me to where I am today in my current state. And in this particular state, I still think it's a good state, but it's a state where being a prime minister is not one possible action that I can choose from. Okay, so in reinforcement learning, yeah, these are the 3 points, and we have a full course on this where you'll learn a lot more and you'll get to build very interesting applications. So I just give a simple example to show actually the difficulty of reinforcement learning. Okay, so right now, I have two results. Okay, this is a GIF result. This is a classic toy example. In reinforcement learning, often we work with toy examples. Why is this so? Okay, because they are already well-established benchmark. So you know whether your code is so-called successful or not successful. How many points is considered a success, right? That we have established benchmark, and this is why people normally compare their models on all these known so-called toy cases, okay, with known rewards. So in this particular scenario, what happens is our action space is always four possible actions. Okay, we just want to do nothing. Okay, the objective is a space lander, okay, a lunar lander that is trying to land on the moon. So we have a choice of doing nothing, which would mean that gravity gradually brings your lunar lander down, or you want to move left or move right or fire your main throttle, okay, to go up. The objective here is to navigate yourself such that you're able to land between the two flags, but not too quickly. Because if you land too quickly, you will end up crashing. And what happens is there's already a well-defined point system, right? On the right of this slide. If you land safely, it's 100 points, but if you crash, it's a negative 100 points. Okay, so the objective is just to try out many different simulations and learn what to do under different scenarios. For example, when you see that, oh, I'm descending too quickly, then I better fire my main thruster, okay, to slow down. Okay, if I'm too far away from the flags, then probably I want to fire in the other direction to get back to the center. So again, let me just go back and forth just to show you this example. Okay, the difficulty about reinforcement learning is that these two models are actually from the same code, okay, but with some different hyperparameters. So what happened was that the scenario on the left, we trained the model such that it is so conservative, it does not even dare to go near the ground. Okay, so in the short term, it thinks that it's doing fine, right? What happens when you fire your main engine? It's a minus 0.3 points. And when you fire a side engine, minus 0.03 points. So the case on the left is a typical example of reinforcement learning whereby you start encountering failures early on and you are so afraid of the failures that you do not dare to try anymore. And in this case, it simply gives up trying to approach the ground. It just keeps firing its main thruster to stay as far